Welcome, everyone, to the third public science panel brought to you by the University of Washington's astrobiology program. Thanks for joining us live on YouTube, where you can follow the UW Astrobiology channel, which is full of lectures and videos all about astrobiology, including our previous public science panels about the best places to look for life in the universe and the origin and nature of life itself. My name is Mike Wong, and I am a postdoctoral researcher in the UW Astrobiology program, and I'm joined tonight by four of my fellow scientists who are all driven by their curiosity about the possibility for life in the universe. Are we alone in the universe is one of the greatest outstanding scientific questions. And amazingly, our generation may be the first to have the capability to actually find evidence of extraterrestrial life. But it won't be easy. Tonight, we'll meet four astrobiologists who are actively engaged in the search for life. Our panelists are experts in different approaches to unraveling this multidisciplinary scientific problem, and they will share their insights in a moderated discussion, which will last about 40 minutes, and then answer your questions in the final 20 minutes, which you can type into the chat box on YouTube. I'll also advise you to pay close attention to what the panelists say tonight, because there will be a fun and friendly competition where you can showcase what you've learned during the panel, and I'll reveal a bit more about that later on. So without further ado, let's begin by getting to know our panelists. So panelists, please say a few words about who you are, what you study, and also if you might share your favorite fictional alien with us. So Sam, why don't you go first?
Hi, everybody. My name is Samantha Gilbert. I am a third-year PhD student studying how we can quantify our confidence that we've detected signs of life in the atmospheres of faraway planets. And I think my favorite alien is definitely Gonzo from the Muppets.
Wonderful. Zach, why don't you go second while Kim Bot finishes laughing?
Hi, everybody. My name's Zach Cooper. I'm a sixth-year PhD candidate in oceanography and astrobiology at the University of Washington. I study very tiny things that live in some of the most extreme environments on Earth, so very specifically extremely cold and salty brines that we find in ice in the poles of the Earth. It's very fun. My favorite alien is probably Dr. Zoidberg from Futurama. I like him. He's funny and he loves the ocean and just having a good time. So it's great.
Wonderful. Yeah, an ocean alien for an oceanographer. Kimberly Sinclair, how about you go next?
Hi, I'm Kimberly Sinclair. I'm a second-year graduate student in Earth and Space Sciences and Astrobiology. I study the origin of life, specifically in surface lakes, both on early Earth as well as on Mars. And so I do operations on the Perseverance rover, trying to find signs of past life on Jezero Crater, which is an ancient lake bed on Mars.
And last but not least, our alum for tonight, also a Kimberly, Kim Bott.
Hi, as Mike just said, I'm Kim Bott. I'm a postdoc now at University of California, Riverside. I was recently a postdoc at UW in the astrobiology and astronomy departments. I study mostly polarimetry. So however, the method of polarimetry can apply to studies of habitability or detecting life on other planets. So I kind of have like an instrumentation approach to things and try to apply it to as much as I can. My favorite alien, you guys have had such cute answers. Mine's so serious. It's the planet in Solaris, because they didn't even realize that it was alive at first.
Ooh, that's a good answer. Yeah. a planetary biosignature. Maybe we can talk about that later on, as well as polarimetry. But yeah, we're all here tonight because we all want to know if we're alone in the universe or if we share this cosmos with beings like or perhaps unlike ourselves. And to do so, we scan the heavens and send robotic proxies to explore strange new worlds in search of biosignatures, which is a word that might be unfamiliar to some folks out there. So let's begin by defining that term biosignature. Panelists, what is a biosignature?
Well, that's a hard one to answer because it depends, or at least I think it depends on how we define life. So what in general, a biosignature should be something that tells you that there's life or there's likely to be life on another planet. So if you know that life needs to breathe out certain types of gases or something like that, then you go and look for those gases on another planet. Or if you know that the light always reflects a certain way off of a living material, then you go and look for that signature of reflected light. But if it's a really good biosignature or not depends on how you define life. So I feel like there's kind of a caveat. Does anyone want to add to that?
Yeah, please jump in.
I agree with Kim's definition. And when I was trying to think of my definition of a biosignature, I also confronted the problem of trying to come up with a very generalized definition. So the one that I tried to come up with is basically some chemical or physical indicator that may point to the presence of life on a planet or moon, depending on the context of the planet or moon's environment. And for me, chemical or physical, or, you can play around with those words all you want, but the really important thing, the key piece of my definition is the dependence on the context of the planetary environment. And this basically involves asking ourselves if the thing we've observed, be it a chemical or physical indicator, cannot be there without life producing it, given everything we know about said planet or moon. So basically asking ourselves, is the thing that we've observed strange, given what we know about the planet or moon that we're studying?
That's excellent insight. Yes, absolutely. Zach or Kimberly Sinclair, just wanted to see if you had any thoughts on biosignature definitions.
Yeah, I think that both of these points from Sam and Kim are great. I think that, a biosignature in a very, very plain sense is, just a signature of life. That's the name of it. It's a footprint left behind by something that's alive. How can you tell what it is? But I think, one added point of this that I think about a lot is that any one biosignature might be kind of hard because you can say, oh, there's something that seems a lot like maybe it was produced by life, but it's hard to say on its own, so this is something that happens a lot. We see something very exciting in the news, but we're like, we want to confirm it a few ways. So it's also inherently a set of a couple of things. Biosignature, I think, needs to be plural.
Yes, multiple lines of evidence pointing to the same thing.
Yeah, I guess the only thing I'd add, because I agree with everything being said, is that it can be very simple and it can also be very complex. So you can have everything from actually finding a microbe versus finding an organic molecule, or even just finding a mineral in a rock that is very indicative and could not form without interaction with life. So it spans a wide range of complexity as well.
Yeah. And I feel like today we're going to examine a wide range of different types of biosignatures. So let's dive in and begin with the red planet, our next door neighbor, Mars. When I was 5 years old, my mom showed me a newspaper headline about scientists discovering microbes on a meteorite from Mars with a black and white photograph of what looks to be a microscopic cell. So let me go ahead and see if I can share that image with folks. And hopefully you're all seeing that now. And so, this discovery was so big that it even made it into a speech by then President Bill Clinton. But over the years, the scientific consensus has sort of shifted. So, Zach, you mentioned that you study microscopic life in extreme places. And honestly, I can't think of anything more extreme than getting knocked off of a planet by a giant impact, riding on a meteorite through space for who knows how long, and eventually crash landing on Earth. So could you tell us a little bit about this image and why it isn't a sign of life?
Yeah, thanks, Mike. It's really interesting. What a fascinating idea to, like just be living your life and then you're launched across the solar system to who knows where. So when I look at this though, I see what I want to see immediately because I'm a microbiologist and I look at it and I'm like, oh wow, that looks like a bacterial cell or an archaeal cell or something that we know like that, and it's pretty convincing, and that's really exciting. What I don't have on the image here that I wish we had is a scale bar to help you get a little reference. I think and I believe that these shapes are in the tens to hundreds of nanometers size range, which is very, very small, like maybe even smaller than most bacteria that we know alive right now. And so I would be convinced maybe by an image alone, but this goes back to, our discussion we've already been having about biosignatures is maybe I want a few more lines of evidence to prove to me that this is in fact a bacterium or something like that, or what we know as something alive. So it looks really cool, but I've also learned in my years, and I'm not a geologist, so take this with a grain of salt, that geology can play tricks on you. It can create shapes that look a lot like maybe they were alive at once, but then aren't always the case. Or, I can imagine trying to live on that meteorite as it was launched from Mars. And maybe I can envision living for a little bit of time out of the atmosphere into space if you're deep inside the meteorite and if you're already growing pretty slow. It could happen. There are bacteria that take thousands of years to live, but this picture alone, I think, is interesting, but I would definitely need more information. I know that there was some chemistry done on this rock, but it's close, but inconclusive.
Yeah. Well, thank you for that insight, Zach. We astrobiologists, we're impatient folks. We don't want to wait for Mars rocks to come to us. Instead, we take the search to the red planet itself. And earlier this year, we all celebrated the Perseverance rover's successful landing on Martian soil. Kimberly Sinclair, you mentioned that you work on the Perseverance rover. In particular, you work on the Pixel instrument. And this mission is currently charged with trying to find life on Mars. How exactly do Pixel and the Perseverance rover look for signs of life?
Yeah, so the Pixel instrument is one of 7 instruments on the rover. There's a lot of science going on that rover. Pixel stands for Planetary Instrument for X-ray Lithochemistry, which maybe isn't very significant to remember, but it's a fun acronym. I like it. And what Pixel does specifically is it goes up to the rocks and it shoots X-rays at them. And based on how X-rays interact with different atoms, you can get a chemical fingerprint of what the rocks are. So you find out the elemental composition of all of the rocks on the surface. And we also have a camera on the instrument that takes images at a really fine scale, like you can see grains of sand. So you can both determine the chemical and like physical alteration of the surface that could have been caused by ancient life. So we focus a lot on chemistry and also morphology, so the shape of rocks on this instrument. But of course, there's 6 other instruments on the rover, and they all do different things as well. One of the instruments looks more at organic compounds, so that's the Sherlock instrument. It's also a spectrometer, so it also shoots light at the rocks in order to determine their composition. And obviously looking for organics is very significant for looking for signs of life. And there's also cameras, very, very good cameras that are better than the camera on the Pixel instrument that look at high resolution images and determine signs of life as well. So yeah, there's a lot going on the rover.
That sounds like a lot of fun, zapping things on Mars to find signs of life. Perseverance is also the beginning of this long-term effort to bring scientific samples of Mars back to Earth. Kimberly Sinclair, when can we expect these samples to arrive back here on our planet? And what do we gain by bringing more of Mars to us?
Yeah, so I guess the short answer is as early as 2031, although likely much later. It's a complicated system. So basically we've sent the first of 3 stages already in this system, which is the Perseverance rover, which is collecting rocks on Mars and putting them into tubes. And so there's this system called the sample caching system on the rover, which is in charge of picking up these rocks and sealing them, hermetically sealing them in tubes, and then leaving them on the surface of Mars. And of course, we are very particular about which rocks we choose to leave in these tubes because we only have something like 40 tubes and likely we'll only get about 20 samples or so in tubes at the end of the day. So we choose rocks very specifically that we think might be interesting to analyze on Earth. Like, for example, a clay would be really interesting to analyze because clays often will store organic molecules in them if it was a lake. So it was a lake bed in its history, could have had organics in it maybe. And a clay is a really interesting thing that we'd love to bring back to Earth to study further. So we choose these rocks and we cache them in these tubes, leave them on the surface. And there's 2 more missions that would then go on to collect and bring back these samples. One mission would be the Mars Sample Return mission, which would go land on Mars, collect the samples, and use a Mars ascent vehicle to shoot them back into orbit around Mars. That would be, around 2028 when it got to Mars, hopefully. This is funded jointly by NASA as well as the European Space Agency. So there's a lot of different factors at play, I suppose. And then the 3rd mission would be picking it up from orbit around Mars and bringing it back. And that would hopefully land on Earth in 2031, to be determined. And having these samples back on Earth would allow us to perform like much, much more extensive analyses than what we're able to do on Mars. That's just because we have laboratories on Earth that are much more complicated and heavy, that would be impossible to take to Mars. And so by having these samples stored on Earth, we're able to do more complex analyses, but also if we have them stored here, as we develop instrument technology in the future, we can keep coming back to them. And as our technology advances, we can learn more and more. So that would be great.
That's a really, really great point. And yeah, can't wait for 2031, crossing all the fingers and toes that the samples actually come back. So we already met this controversial Martian meteorite, ALH 84001, today. Another Martian controversy involves the detection of methane in its atmosphere. Now, Sam, I know you've looked quite extensively into this. First of all, why is methane an exciting gas for an astrobiologist? And what should we make of this mystery of methane on Mars?
Yay, methane. We love methane. So methane is such a great gas to look for when you're searching for signs of life on other planets, because basically life is the only mechanism that we know of, at least right now, that can produce methane very quickly and in enormous quantities. So here on Earth, there's all kinds of life forms that produce methane. So if you're paying attention to the growing climate crisis, then you know that there are a lot of anthropogenic or human pollution sources of methane, like landfills, oil, and natural gas. And you've also probably heard that cow farts are actually a pretty significant source of methane on Earth. And then there's also really simple life forms that produce methane too, like these communities of bacteria called methanogens that have actually existed on Earth for hundreds of millions of years. So we have a ton of examples of Earth life throughout our planet's history, producing enough methane that it actually accumulates in our atmosphere to observable abundances. And that answers the question of why we think it could actually be a really good gas to look for on other planets. But the mystery of methane on Mars is a great example of why looking for methane as a biosignature, even on a planet that's right next door, is no easy task. So for context, what Mike was talking about is that methane has been detected on Mars using telescopes here on Earth, spacecraft orbiting Mars, and rovers on Martian soil, the kind that Kimberly Sinclair works on. So what's weird about this Martian methane is based on these various observations that we've done, it looks like it goes away really quickly. And also the amount of methane we see appears to vary seasonally. And as of right now, we really don't know of any chemical processes in Mars's atmosphere or on Mars's surface that could explain the observations of methane on Mars or its weird transient behavior. So naturally, some people have proposed, including scientists, that this methane could indicate some sort of methane producing or even consuming life existing on Mars. But there are a few problems with this theory. So first, there's reason to doubt that these detections are real in the first place. So in other words, there's reason to doubt that our telescopes and rovers, or there's reason to believe that our telescopes and rovers might be falsely detecting methane where there actually is none, or that even our analysis of the data could be wrong. So scientists heavily debate the point of whether or not the methane is truly there to begin with, and that's an important point. But then even if you accept that the methane on Mars is really there and we've correctly detected it, there are still a lot of other obstacles to the conclusion that there's life on Mars. So the biggest obstacle is that there are many abiotic or non-life processes that can also explain the tiny amounts of methane we've observed and its strange behavior. So for example, there's a special configuration of ice called a clathrate that can actually trap methane inside it and then release it later when it melts. So this would allow methane produced in the past on Mars to be stored for later release. And we now think that Mars used to be much wetter and potentially more volcanically active in the past. So it's totally possible that you could have had some hydrothermal volcanic process on ancient Mars that could have generated this methane. And then this ancient methane became trapped in the clathrates. So this is just one possible mechanism for explaining the transient methane we've observed that doesn't require life at all. So to conclude, what methane on Mars teaches us is that before we can even come close to suggesting that we found a chemical indicator of life on another planet or moon, all of the possible abiotic explanations have to be completely exhausted first. And that's why this discussion of methane on Mars continues to rage on, even though some of these detections happened 20 years ago at this point. So methane on Mars is a really good example of why looking for biosignatures is such a tricky and complicated task, and why these cases will likely never be open and shut. If we find something interesting on another planet, we will almost certainly be debating it for years and years to come before we come to any sort of consensus on what it is or where it came from. But that's just the scientific method.
Indeed. Thank you for that whirlwind tour of methane on Mars and how it really highlights so many of the important issues at stake when we are trying to find evidence of life on other worlds, Sam. You mentioned that methane, though, in principle, is a really good gas to try to look for because it can be created by life really, really quickly. So let's now turn our gazes afar. When searching for life on exoplanets, which are worlds that orbit other stars beyond our solar system, the easiest biosignatures to detect will likely be atmospheric gases like methane. So Sam, could you quickly explain the techniques that we would use to characterize the atmospheres of exoplanets?
It would be my pleasure. So to study the atmospheres of planets that are really, really far away from us, we rely on something that can travel extremely long astronomical distances. And that thing is, of course, light. So there are three main techniques for characterizing exoplanetary atmospheres using light, and they are called transmission, emission, and direct imaging. And what all these methods have in common is that they're all looking for how different molecules like oxygen, carbon dioxide, methane, what have you, in the planet's atmosphere absorb or emit energy to actually alter the light we observe when we point our telescopes at an exoplanet. So the technique that we choose between these three options depends on the planet we're trying to observe, its size and distance relative to its host star, and then also the geometry of how we'll observe it from our particular position in the galaxy. So in the near future, we're going to get our very first glimpse of the atmospheres of Earth-sized planets. And these first glimpses of rocky planet atmospheres are going to use the transmission technique. And so in the transmission technique, we point our telescope at a star and we wait for the exoplanet we want to observe to pass in front of it. And as the planet passes in between our telescope and the star, some of the star's light will actually skim the top of the planet's atmosphere on its way to us. And if you want a better visual of this, you can just imagine my big head blocking the star in my background here. That's sort of what it looks like. And so we study how the planet's atmosphere changes the star's light to figure out what chunk of the planet's atmosphere contains. So this raises a really important limitation of transmission because we're studying the star's light as it passes through the very top of the atmosphere. So we don't actually know what's happening on the surface. And this makes it difficult to figure out what planetary processes, including life, could be happening there. And then also because we're looking for how the star's light changes as the planet passes in front of us, it's really much easier to do this technique for planets that are really big and really close to a smaller star. So this means we wind up studying Earth-sized planets that are orbiting stars much smaller than our sun. But ideally, we really want to study Earth-sized planets around sun-like stars, since that is the one example of a system that we know has life. Fortunately, in 20 to 30 years, we'll get to study the atmospheres of Earth-sized planets around sun-like stars with the direct imaging technique. And just like the name, this technique points the telescope directly at the planet instead of at its star. So we can probe straight down through the planet's atmosphere to its surface. And this will allow us to get a peek at the processes that are happening on the planet's surface, which arguably gives us the most information possible about potential geological or even biological activity that's happening there. And what's also exciting about this method is that to be able to study the planet directly, the planet actually needs to be far enough from the star that we can distinguish the planet from the star. And this is what allows us to go after the atmospheres of Earth-sized planets orbiting sun-like stars, rather than the sort of less ideal systems that we're able to study with transmission.
Wow, that was a lot of great info. And it sounds like it'll be a long journey trying to look for signs of life on exoplanet atmospheres. But you know, the case study of methane that we just talked about for Mars might make somebody very worried about exoplanets. I mean, if there's so much controversy and uncertainty about whether life is breathing gases into the atmosphere of literally the world next door, what hope do we have for identifying and interpreting possible signs of life on planets many light years away that we can never hope to send a rover to? You know, Sam and Kim Bott, I know you both study exoplanets. How would you respond to all the doubters out there?
Well, as Sam was bringing up earlier about the methane, that ended up being a great trial to kind of learn about all the caveats, all of the little details that we need to look for. People say there's the known unknowns and the unknown unknowns, and getting these examples of things like methane on Mars and phosphine on Venus kind of lets us go through this scientific process where we go, okay, we see something that looks kind of like it could be from life, and let's, you know, cross all our T's, look for, as Zach has brought up, other signs of life there, other biosignatures, as people have brought it before, look for the context. Does it make sense in this context? So I think to the doubters, I wouldn't say that, you know, these examples in the solar system turning out to not be life are bad things. They're just teaching us some extra steps that we need to do along the way.
That's an excellent point. Yes, we're learning so much from our solar system planets that we can then apply to the techniques to search for life elsewhere beyond our solar system. Sam, did you want to add to that at all?
Yeah, definitely. I think Kim makes an excellent point. Any exoplanet scientist worth their weight will absolutely be thinking about solar system bodies and the lessons that we've learned from looking for biosignatures there. The other thing I'd add is, because we can't go to these exoplanets in person, part of the problem is that we really rely on computer models to interpret the data from exoplanets. If our models are bad, then our interpretations are bad. And it's actually very, very hard to know when our models are bad. But the good news is that because we're going to be getting this high quality data in like 2 to 3 decades, we have a lot of time to continue building up our models and validating them. Because again, it's going to be a couple decades before we actually get access to this high quality data. And this means that when we do get that data, we're going to be in the best position possible to interpret it with the confidence that our models work and are reliable. That being said, to the doubters, I think they're kind of right. And I think that's okay. I think being a doubter is good in science. We may never be able to say definitively whether or not a faraway exoplanet contains life. But the key is to recast the question of, is there life, in terms of probabilities instead of in terms of a binary yes or no. So being able to assign a probability, a number, to our confidence that we have, for example, detected oxygen in an exoplanet atmosphere, and to then assign a probability to our confidence that that oxygen indicates life for that planet's unique context and environment. All of that will really be key. So as we get closer and closer to truly probing the galaxy for extraterrestrial life, it's going to be super, super crucial to develop a framework that we can use to quantify our confidence that we've detected signs of life or not.
I really like that reframing of the question. You know, it's not a yes or no question, but it's about a gradient of confidence of detecting life. Now, Kim Bott, you are one of the world's experts in polarimetry. First of all, what the heck is polarimetry? And second of all, how can it be used to increase our confidence that we have found life both elsewhere, beyond our solar system, and also within our solar system?
Okay, just like 3 questions there. So polarimetry, I don't expect most people have heard of it. You probably heard of like polarized sunglasses or something, and it has to do with that. It's just measuring an extra aspect of light that's always there. So a lot of people in the audience today probably have heard this idea that you can think of light as a wave. And normally if we're measuring light, especially from stars and exoplanets, we're looking at maybe the intensity of light, how bright things are, So how big the wave is. We're looking at the wavelength of light, what the frequency is. Is it a short wavelength going up and down really quick, or is it a long wavelength going slowly? And that's the color, the spectrum. There's this other aspect, that's its polarization, and that's just telling you how the light is wiggling. Is it oscillating up and down, side to side, in a corkscrew, or does it not really have a preference? So that information is always there, and it's just not always measured because at least in the past, it's been kind of complicated to measure it. Maybe we're getting better at it now. Some of the places that we could apply this in astrobiology, both for exoplanets and in our solar system, is in particular in characterizing clouds. Polarized light measurements are particularly useful at figuring out what the species of cloud is, and the size of the droplets, if they're kind of spherical droplets, or if they're a haze, discerning between those things, discerning between whether or not you're reaching a surface, your remaining light is absorbed into a dark ocean, or it's reflected off of cloud and not reaching the surface. It's quite useful in that regard. So what Sam was talking about earlier, where with transmission, you're just getting information from the upper atmosphere. If we're looking at reflected light, in some cases, it's still kind of hard to tell whether or not you're getting light reflected off the surface or off of a cloud. That was an issue in characterizing Titan in our own atmosphere, a moon of Saturn. And with polarimetry, people were able to say, no, this is definitely a haze that we're seeing the light reflect off of, and it's, like a hydrocarbon haze. It could also be used to help us pick out these gaseous biosignatures that we've been talking about before. You can do spectropolarimetry, just like you can take a unpolarized spectrum. And there's some scenarios where that might be a little bit more helpful, or picking out things that are just really strong polarizers, like the rainbow and the glint off of an ocean. So if you're looking for just kind of a habitable environment that has things that we think life needs or that life would really like, you can look for that glint off an ocean. You can look to see if that glint kind of blinks on and off as the planet rotates, and continents, if you think continents and plate tectonics are something that life would like or that life requires, you could possibly apply it there to get just a slightly more clear observation of glint off of an ocean than if you were not using the polarized light. In our own solar system, we could look for a biosignature with polarized light, because life tends to make molecules that are kind of all wound up the same way so that they can, contain information and keep interacting with each other in a consistent way. Like our DNA all winds the same way, our proteins all bend the same way. And that tendency for everything to bend the same way, if you reflect light off of it, imparts a polarization. So it tends to make the light reflecting off of it corkscrew in a particular way. And so that's something that people have suggested maybe using on icy moons in our outer solar system. Can we send a polarimeter there, or maybe in orbit, to see if there's this tendency for the light to corkscrew in a particular way, not very much in the other way? And maybe that would tell us that there's something living there. And that's kind of like a broad definition of life, right? Like, it doesn't have to be life just like us. We just think that life needs to make some kind of chemical molecules that contain a lot of information, and they need to work in a consistent way to maintain that information over time and pass it on. So we think that's kind of a broad agnostic biosignature to look for that, those chiral molecules from circularly polarized light.
That's certainly a mouthful, but yeah, who knew that light could corkscrew and tell us whether or not it's reflecting off of living or pieces of molecules that were inside of a living entity. This brings a really great question to mind. So you spoke about doing that for maybe a robotic visitor to Enceladus or Europa, one of the icy moons in the outer solar system. I want to know from Kimberly Sinclair and Zach, besides these cool polarimetric measurements that Kimbot wants to make, what other kinds of things would you try to look for on those kinds of worlds to find evidence of life? Yeah,
I have some thoughts. I have a lot of thoughts. I love icy moons because I love life in ice. That's everything I study. I think that, yeah, polarimetry is great, and if we can find some clear signs of chirality or molecules all spinning the right way, that would be really interesting. I think actually, Kim, you touched on one of the key things that I think that we can define as a really universal concept of what life is at a very basic level. And that's, these molecules that contain all of the information that tell life what to do, and that they're repeated and that they're consistent and then they work. So Kim, you mentioned DNA. DNA is what every single living cell on Earth uses. And these are these polymer molecules that repeat sequences and they encode information. And so if we could send a robot to Enceladus or Europa and have it look for molecules at some like greater scale that have obviously repeating and organized and clear structures, that would be a pretty good additional signature to me. Another signature that I think about that's, I think, maybe more on the physical side of life than just molecular stuff is looking at actual particle movement. And so if we can send a sort of microscope or something and then get some of the brine from inside of our ice or melt some of it and see for water, we can look for non-Brownian motion. And so that would tell us if there's something moving against the laws of natural physics, or it would move on its own. So, I can move my hand here. That's non-Brownian. That's my hand not moving the way Brownian motion works. But yeah, if we can find that, that's every single thing we know, almost everything we know alive has some motal action. And so that would be a good thing that I would like to see as well.
Yeah. That's so cool. Kimberly Sinclair, did you have any additional thoughts for how to find life on Europa and Enceladus?
Yeah. So I love all of Zach's ideas. I think a couple others could be looking for isotopic indicators. So organisms tend to prefer a specific isotope of carbon. So an isotope being an element that has a different number of neutrons in the nucleus. And so by looking at the specific isotopic ratios, you can determine the likelihood of life as well. Looking for biominerals. Of course, this is a big thing for me on Mars, but also applies on ocean worlds. Looking for those minerals that would have been formed by the interaction with life. And that can be really interesting as well. Yeah, I guess those are most of them, though. I think we've covered a lot.
Lots of options to go searching for life in those worlds. Zach, I wanted to ask about your travels to Antarctica to look for life that could resemble life living on Europa or Enceladus beneath those icy shells of those cold satellites in the outer solar system. So in your surveys, who is actually living in Antarctica, and how do your investigations ground our search for life elsewhere?
Yeah, thanks, Mike. Besides penguins and all of the large, cute animals that we know and love from Antarctica, actually what is really interesting in what I study is the stuff that lives inside of the ice that grows in the ocean there. And so this is a really fascinating thing to me. When seawater freezes, you form sea ice. And this is a pretty common feature throughout both the Arctic and Antarctic oceans. And in Antarctica, you can find sea ice completely surrounding the continent, and there's a lot of space inside of it because there's all sorts of material in seawater. There's salts and organics and living things, and the sort of living things that actually can make their way inside of the ice are mostly what we call microbial or microorganisms that grow in the micron scale. So there's a reason for that. So these things include diatoms, which are types of algae, or bacteria and tiny viruses, so bacteriophage and diatom viruses. And in these very extreme environments inside of the ice when it's very cold, mostly what you find are these microbial communities completely living on their own with their whole entire food web kind of encapsulated together, just living inside of the ice and making a home out of that. So when we look at Europa or Enceladus, what we probably have is all this sort of ice that was made from this watery material that's not pure. So I can expect that we probably will have some sort of brine system at the bottom or inside of the shell somewhere where maybe we can have life that's microbial and tiny, these like hard to see communities living there. So That would be
That's really, really cool. I'm very jealous of all your field trips to Antarctica. It sounds like an amazing time.
really
We're at the point now where we need to open things up to the audience and also give the audience a chance to have an interactive aspect to this panel. So today we saw a headline claiming the detection of life way back when we were talking about that Mars meteorite. But despite that headline and others like it, I think one thing that we can all agree on is that we haven't yet found conclusive evidence for extraterrestrial life. But over the past 40 minutes or so, you've all heard about numerous avenues that scientists like our brilliant panelists tonight are pursuing in search of that evidence. So tonight's interactive task is to imagine the day that we do find unambiguous, definitive evidence for life elsewhere, and to put yourselves in the shoes of a science journalist. So the prompt is to write an imaginary newspaper headline describing that first discovery of extraterrestrial life, and bonus points will be given for using concepts that you learned today, as well as just being creative and entertaining. So please go to tinyurl.com/AB headline. That's tinyurl.com/AB and then a hyphen and then headline to submit your imaginary newspaper headline from that future day when we discover unambiguous life elsewhere in the cosmos. And now it's time to take questions from our audience. And I always have to start these off with an apology if I accidentally mispronounce your name, but there are some great questions here. And so let's just get started. So Emir Guzotok, really like 100% confident that I mispronounced that one, so I apologize again, asks, what do you all think about the possible biosignature phosphine on Venus? Would anybody like to take that one?
I can start, but I certainly do not think that I am the most qualified person on this panel to address this issue, but that's sort of the elephant in the room tonight, isn't it? Phosphine on Venus. And it sort of followed a very parallel track to the detection of methane on Mars. So if you're interested in predicting the arc of how this story will go within, scientific discourse, then, really study up on what happened with methane on Mars and what's happening with methane on Mars, because I'm sure that the same thing will happen with phosphine on Venus. So I think a great paradox that phosphine on Venus brings up is what I said about looking for signs of life that make sense for the context of the planetary environment. And one example of that is looking for, some sort of gas that it's really hard for life to make, given what's chemically available in the atmosphere of that planet. And so phosphine should thermodynamically be very, very difficult to make on Venus. And so that's why it's, potentially an attractive biosignature. But part of the problem is that we really don't understand a lot of Venus's chemistry. So it's very hard to definitively say, first of all, whether the phosphine is really there. If you really get into the weeds of how the observations worked, it's very complicated. It's very difficult to interpret the data. So it's possible that the phosphine wasn't there. If it is there, then there are a lot of unexplored abiotic pathways that could have also generated that phosphine. So there are definitely a lot of obstacles to concluding that, phosphine definitively signals that there's life on Venus.
Yeah, thank you for that, Sam. Yeah, difficult question because it's active science right now, right? This is something that people are working on at this minute, I'm sure. Trying to understand the processes that could contribute to phosphine on Venus, both biologically and abiologically. Great question, Emir. AC asks Dr. Bott, what about the red edge signature? So Kim, do you want to just quickly explain what the red edge is, and then if that's a promising avenue for searching for life?
Yeah, okay. So the red edge is an absorption signature from the, sorry, I'm like forgetting words right now, from the molecules that life uses. Why can't I think of that? Like chlorophyll, that kind of stuff.
There you go.
Whatever those are generally called. Anyway, so it's this sudden change in the amount of absorption in the red part of the spectrum from the type of molecules that life uses to absorb certain wavelengths of light and not use other wavelengths of light. So people have pigment. Geez, okay, pigment. So people have suggested looking for pigments like this, or if you're around another star that has kind of a different shape to its light output, that maybe outputs a little bit more blue or a little bit more red, whatever we anticipate life would use to use light in something like photosynthesis, whatever we think that pigment would absorb, what wavelengths it would use and what it would throw away. People have suggested looking for that in the reflected light spectrum off of a planet, because it's this really big feature. You're not just looking for a little line or something like that. It's this sudden shift, relatively major shift in the light that you're getting from a planet. Was that the question? You just wanted me to explain what it was? What about it?
Yeah, and if you think, I guess it's a good avenue for searching for life elsewhere.
Yeah, it is. Like all the other biosignatures we've talked about today, it has to be taken in its context. There's some non-living mineral sources, some other things that could be producing a similar kind of sudden shift in the reflected light from a planet's surface. They're slightly different. So people have said, oh, if we look a little more carefully right here at this wavelength, and maybe take an extra band, an extra measurement right here, we could probably tell these things apart. But yeah, I think it's great. It also just needs to be taken in context, but it's a good one. And I think that's another one that you would see in polarized light, so I like it.
Nice. Yeah, thanks for that, Jim. It's hard being put on the spot, right? Sometimes words just flow out.
Terrible. I forget words all the time while I'm speaking.
No, you did great. That was awesome. And now from Jeffrey Needle, what would be the most convincing combination of elements or molecules as a biosignature? Maybe Zach or Kimberly Sinclair, you can weigh in on this one. A combination of molecules or elements.
Yeah, I can say some things about that. I think it's really fascinating. I think to start with, what we would think about with this is what we know on Earth. So in biology, at least, we always have to make a lot of assumptions about what we're looking for, what we're looking at. And so if we want to look for a combination of molecules, I'd say, like, if we, just a one good educated guess would be to look for things that look like what we have on Earth. And so a cell on Earth, a very simple cell, like the kind of stuff that can live pretty efficiently in extreme environments, is made of a membrane that's mostly fatty acids, an interior that includes a lot of proteins and DNA molecules. And really, that's most of it, right? So if we want to look for molecules that will definitively tell us, we want to look for these larger organic molecules like fatty acids or amino acids that have formed into proteins, things like that, and these sort of repeating ones. So in a very ideal scenario, we find exactly the kind of chemistry we know and love from Earth. But I'm sure there's a lot of ways to do it. I mentioned earlier, I would love to find just repeating information polymers. That would be one really good signature just to start out. But yeah, Kimberly, do you have some additional thoughts, answers?
I think that's a tricky question because, in terms of organics, there's a lot of promising organic molecules. I think finding any organic molecules, like complex organic molecules, would be very exciting. But in terms of elements, that gets more complicated because no single element is going to tell you, oh, there's life here, right? Because at least in a lot of the work you do in geochemistry, it's a matter of a mixture of elements, and if those mix of elements would imply a specific mineral that would imply maybe certain conditions, which would imply life. So it's a bit more complicated than, I guess, specific elements sometimes. And like Sam has said a lot, it depends on the specific situation, the context of the planet or moon that we're looking at. Sorry, I know that's not a very satisfying answer.
All right, thank you both for your thoughts. Rui Gatto asks, if you find a planet with water, is that a good indication that life is there? Anyone want to take that one?
It's a good sign. So that's, well, we often discern between like habitability markers that tell you that an environment is friendly to life and a biosignature that we think is directly from life, even though it still has to be taken in context. So, I mean, water, we need some kind of solvent, some kind of liquid thing. Water does a really good job of not only that, you can tell I'm not a chemist, not only that, but a lot of other things that life kind of needs it to do. So not only being a solvent, but like something about it, like its polarity. I don't know, Zach or someone else probably can like answer that better than me, but it's very good at that. So having like a water clouds and water ocean, water in the atmosphere, if you saw like all of those things, like not just in ocean, but you also saw that there was like a water cycle on a planet, I would think that that's a pretty good sign for additional reason. I'm sorry. Additional, my brain is just trailing off on like all of the uses of water in a water cycle. So also just like being able to store up greenhouse gases with a water cycle and the runoff, and having oceans and plate tectonics to like tuck those things away for a long period of time and stabilize your atmosphere. There's just, it'd be really nice if there's water. That's a really good sign.
Zach, I saw you unmuted.
Yeah, I can say some stuff about water too. I think it's great for a lot of the reasons that that Kim mentioned. But you know, when you think about the individual cells, one really big thing I think that's just right off the bat is almost anywhere on Earth that there is water, we find life. And so I think that that's one of the biggest tipping points. And so when I say like extreme environments, I'm talking about these physical or chemical settings that really push the limits of what we understand life to be able to live at. But we can find waters that are, you know, below the normal freezing temperature of water, so below 0 Celsius, that are still liquid. And because we have liquid water there, life can still swim around and move in it. And on the other side of the temperature range, we have water at the very bottom of the ocean that can reach several hundred degrees Celsius. And you can even find organisms swimming around and living in those waters there. So just as a starting point, as information that we already have on Earth, it's where there's water, there's life, almost ubiquitously. Like it's very hard to get water without something living in it on Earth. And you know, the reason for that to be is that, you know, bacteria, are those like very simple forms of life, don't have mouths necessarily, but they get nutrients from their environment. And so they need to live in some sort of diffusive medium that allows them to collect nutrients and food and stuff from the environment around them. And it gives them the space to swim around and interact and divide and move. So it's really about having space and having the opportunity to get to things.
Excellent. All right. I want to warn the audience that you have 2 more minutes to submit your imaginary newspaper headlines. tinyurl.com/AB-headline. Do that now before we close the poll and select the winners. Okay, let's take a few more questions. So Curtis Takahashi asks, is it possible that we've already found life on another planet, but we just didn't use the right methodology to see it? Any thoughts on this one?
I guess I can say, so there's a lot of debate on past, I'm thinking specifically of Mars, rovers, landers, on, you know, different scientists claiming to have found evidence of life in different measurements. And, you know, there's some debate, some of them are more credible than others. But I think a lot of those come down to the probability of it being a biosignature is just not high enough. And that's what we keep talking about, right? Is it's sort of a statistical measurement. It's not binary. And so sure, you might look like take an image of the Martian soil and find, like we were looking at earlier with the Martian meteorite, something that might look like a bacteria, but you need more than just a picture. You need to know the chemistry, you need to know, there's more information that you need. So I think at least so far, there hasn't been sufficient information or a high enough chance that our evidence has shown life.
Yeah, going back to the multiple lines of evidence and needing to increase our probability threshold high enough. Excellent, excellent. I'm going to close the poll. I'm going to stop sharing this screen now so that we can get the winners on. But let's take another question while I do that. So Anna Armenta Vega asks, what do you tell people that ask, why would you even bother looking for life outside of Earth? This is you're engaged in this pursuit actively. How do you justify yourselves? Any thoughts?
That is a great question. And I'm sure everyone here has a very different and very personal answer for what's driving them to, study this unique field. And I think for me, it just really helps me appreciate how precious life on Earth is and how urgently we need to protect it and protect the fragile and delicate ecosystem that we have that allowed life to emerge, that allows us to be here doing this panel today. So for me, that's definitely the key motivation.
Wonderful. I love that answer so much. Anyone else want to chime in on that one?
Oh, go ahead, Zach.
Okay, I'll build on something that Sam and Kim Bott said earlier. We do all these studies of solar system objects just to get more information. And even if it's not very clear, we're getting information. And so I think that every pursuit and exploration in science gives us more information to get where we want to go. We can't just, find something and be like, that's it, one time, that's it, that's all I know. But I'll say all information you can gain in the field of science is useful to know, and it's informative towards, whenever we do find that real signature. So it's valuable. We have personal different goals too. I just think it's really cool. So that's one really good reason, but there's a lot.
It certainly is cool. Any other last thoughts on this question?
Yeah, I'll just say I think we've gotten very dry in this conversation sometimes about talking about biosignatures. And at the core, most of my peers, I think, would say that we join this field for sentimental reasons, feeling like we want to know if we're alone in the universe, sort of that philosophical question. So I think that at least propels myself and others I've met as well.
Wonderful. All right, so it is now time to talk about where people can find you all on the internet in case they didn't get their question answered tonight. There were a lot of really good questions that we couldn't get to. So let's just go around and say where people can find you and how they can get in contact and follow your amazing discoveries and thoughts about science and life in general. So let's begin with Kim Bott.
I'm so sorry. I was laughing at something in the chat. You want us to tell you where people can get in touch with us, right?
Absolutely, yes.
Okay. So you can follow me on Twitter. I mostly tweet or retweet about sciencey stuff. It's okay. My handle there is humanbot. So like human bot, but with 2 T's because it's my surname. And then you could also follow me on Instagram. I post a little bit about astrobiology stuff and a lot of just kind of nature stuff in general when I do post. And that handle is Endless Slope with only 2 S's in the middle. I need to pick better handles. And then you could always email me. You could look for my email at UC Riverside. Just find me in the department directory.
Wonderful. Thank you, Kim. Zach, why don't you go next?
Yeah, I think one of the best ways to find me on social media is just on Twitter. You can find me at Zach S. Cooper. That's it. It's very easy to find me that way. I have an Instagram, but it's mostly just pets and it's private, so maybe I won't share that one. Yeah, or you can email me, zcooper@uw.edu. And I love talking about science, so I'll answer any questions I get.
Wonderful. Sam.
Yes, so I think the best place to reach me related to science would also be Twitter. So my handle is Exoplanets. So it's like the word exoplanets with an M. I can actually, are our names visible, Mike, to the live audience?
You mean the names at the corner of your Zoom screen? Yes, I believe they are.
Okay, I'm gonna add mine or change my name to my Twitter handle.
Ooh,
Just
that's
to
smart.
make it abundantly clear. Yeah. And then, like Kim Bott said, you can also find my email by looking in the University of Washington astronomy directory.
Wonderful. And last but not least, Kimberly Sinclair.
Yeah, so you can find me on Instagram at Poppy Trex, written is my name now, or email, which is, so my middle name is Poppy, as written here. So my email is kpoppys@uw.edu.
Wonderful. Thank you so much. And I'm going to blitz through this because we're out of time. You can follow UW Astrobiology on Instagram at uw.astrobiology. Don't forget to subscribe to the UW Astrobiology channel on YouTube that you're watching this on right now. And you can follow me on Twitter at MikeY. That's MIQUAI. And before we reveal the winners of tonight's headline competition, I want to throw a special thanks out to our fellow UW astrobiologists, Lucas Pfeiffer, Trent Thomas, and Evan Davis for their incredible behind the scenes work tonight. And let us reveal the winners from our hypothetical headline contest. Cow farts, amount of methane found in Mars, space stakes seem possible, by Anna. Cool. I think you won the funniest competition there. Excellent. Red edge spectral observation of photosynthesis found on Gliese 581G from AC. Someone was listening to the Q&As. Okay. We've got a primitive plants destroy humanity's ego. Purple edge signature seen by James Webb Telescope on TRAPPIST-1e shows that alien plants with precursor to chlorophyll dominate planet, from Veronica Fula. Wow, that's a monster headline, but I'm sure, you know, the discovery of life deserves that many words on a newspaper page. And excellent techno lingo there. Absolutely. I'm really interested in that, you know, precursors to chlorophyll, and can you find like an like a planet that is having prebiotic chemistry on it, not all the way quite to life as well. That's a little bit different from precursors. I'm going on too far. I'm just going to read the next one. Disequilibrium of atmospheric gases on distant exoplanets points to possible life beyond Earth, from a Jim K. I wonder if that's Jim Casting. I don't know. Could be. And finally, and this one I think might be my favorite, technosignature discovered due to pollution from an extraterrestrial civilization, from Mark Ilowitz. So yes, if aliens were looking at Earth right now, they may have found evidence of life, albeit perhaps not intelligent life. Okay, on that sort of sad note, no, just kidding. We are going to Mars next month with our 4th astrobiology panel, Is There Life on Mars?, featuring Andrew Shumway, Yuk-Chun Chan, with alumna Elena Amador French and alumnus Ken Williford. They'll talk to you all about how we're looking for life on Mars right now with the rovers and laboratory work that is going on at the University of Washington and elsewhere. That panel will be moderated by Trent Thomas. So this is my last time moderating a UW Astrobiology public science panel. So I want to bid you all farewell. It's been an honor to do these first 3 for you. And I will see you in the audience on August 25th. So thank you for joining us. Give a big round of applause to all of our wonderful panelists today for their excellent work, and we'll see you next time.